So we're starting building from the ground up. So looking at concrete. So we've got engineers, and they'll look at that soil and look at the building that's going to go on top and decide, okay, this is what we need in terms of a concrete structure for supporting this, or possibly it's not going to be a concrete structure. There are many forms of structure. But if we choose to go with concrete, typically we're going to have to employ an engineer for this because footings are expensive. Good morning. The ramifications of footings going wrong are also incredibly expensive. It's the sort of thing you want to be insured for. So, given that the footings are so important in terms of their design, it's also very important for the engineer to inspect those trenches and the installation of the steel whenever they're being installed. So they're going to want to have notice for when the trench is going to be dug and the steel work is in place, and they'll want to see that before it gets poured. Possibly they'll even want to be on the site on the morning it gets poured. So we've got to have various different loads on buildings, so that's what they'll take into account. They'll take into account dead loads, so all the loads that can be expected in the built form, all the live loads, so what we can expect from the occupancy of the building and the use of the building, the wind loads, so what location we are and what winds we're going to be experiencing, and then if we're building in other areas, we've got to think about things like snow and earthquake, etc. So we've got our compressive forces, which are pushing things together. So gravity acts on buildings as it does on everything that has mass, and it pushes those things together. We also have tensile forces. So tensile forces are things that are pulling things apart. So typically we've got a horizontal beam. We've got the top portion of that beam in compression, the bottom portion of that beam in tension. Then when we've got two opposing forces very close together, that's what's called a shear force. As a result of these forces, we get deflection, so that's displacement away from a straight line. As we covered, as mentioned last week, very important definition, foundation, and footing. So people sometimes refer to their footings as foundations. Technically, that's incorrect. Foundation is the soil or the substrate upon which you start to build. Then the footing, that's the lowest element of that structure. So it's what transfers the forces of that building, whether it be uplift or gravitational loads. The footings transfer those forces onto the foundation. Lots of different types of footings. Construction concrete, so raft, slab, pier and beam, strip and beam, pads and piers. And our choices around that are going to be dictated by the soils that we're working with. So stable soils exhibit little movement, provide a stable base. That's going to be the easiest scenario for building, and also the cheapest scenario for building, because our footings don't have to resist much in the way of loads. Unfortunately, what we get around Adelaide are reactive soils. So that's soils that swell with moisture. So when they get moist, they swell. But also, I guess a lot of the damage is done actually when they start drying out, when they start shrinking, because you get a lot of movement in that clay soil, and you get a lack of support, and things just bend downwards. Things that can cause soils to dry out. Incredibly long dry periods. So we've had a very long dry period right now, and there's been a lot of opening up of cracks and a lot of shrinkage of the highly reactive clay soils around. But also trees. So Australian native trees particularly are really good at taking water out of the soil. And proximity to vegetation, the proximity of trees is also going to be an important thing for engineers to understand in regards to a building. And if you want to be maintaining trees, retaining the trees on that site, the engineer has to know those things, and those things have to be planned for in the construction of the footings. What we don't have a lot of, but something you may encounter in various different pockets, are soft, highly compressible soils are able to support loads. So we've got our Australian Standard 2870 for the design of residential slabs. That sets out the bearing capacity that's required of a soil. Certainly you, as drafters or designers, are not expected to be able to determine the bearing capacity of soil. That's going to come from doing your soil samples and an engineer doing the bore logs and working that out, but it's an important consideration. And then also we've got a few collapsing soils around the place here, so that's typically your wind deposited sands, where you get sands deposited in a random, well, a space in a fashion that includes a lot of air, and where those grains of sand don't fit together well. So I guess, like a little tub of aggregate, they're not sitting all that, there's a lot of air in there. If we give that a little bit of take and add some moisture, etc. to that, we can actually get that to take up less volume. Sand does exactly the same thing. So you've got your grains of sand with their irregular shapes. When you add moisture, that lubricates them and they fit together better, and then they don't have the same, or they don't provide that bearing to the footings, so they can collapse. Really good source of moisture typically is broken down pipes. So you have down pipes for the building taking water from the gutters. It's important that they're maintained well, and if you get down pipes breaking, that is rectified very quickly. Particularly if you're on a sandy site, you can have a down pipe pouring into the sand next to your building, lubricating all those sand particles, getting them to fit close together, and removing the support for your building. Council require a report before approval is issued. There are two types of reports. Your preliminary report. So if you're looking to purchase, or your client is looking to purchase an allotment, then a preliminary report might be important. Certainly, if you're undertaking development like this, a major development, and you're looking at various different sites, that may be an important consideration for you. Typically, a lot of residential purchases don't get preliminary reports done. It's going to cost you probably about $500 to get the soil sampled, and another few $100 beyond that to get that assessed. It's a little bit more expensive, and typically we know that we're dealing with reactive soils in South Australia, and as a percentage of, let's say, the cost of your footings, if it's a medium to high, will be about 12 to 15,000. And then, it's around the 20 to 25,000 if it's going to be reactive for the same sort of footing system. Percentage-wise, yes, you might save yourself a bit of cost, but yeah, typically for a residential application, you're not getting a preliminary report done. However, the council will have to see that report that's designed for construction. So that's where you have to have 3 boreholes done on the property to a depth of 3 metres. Engineers in Adelaide, well, the engineer that I've worked for that's doing bore logs, they like to have their soil samples taken much further down to around 4 metres or so. So 3 metres is the minimum that's required in AS 2870, but for an area like Adelaide where we have deep-seated clays, so clays that extend down a very long way and can take up moisture to quite a distance, engineers like to have those bore logs or those soil samples taken further down. That will dictate what type of footings you have to use. So in terms of the strength of the footings, the steel work, etc., how deep those beams need to be, or how deep we're going to construct piers. So concrete piers. So this thing here I'm holding up. That's just a sample that's a core sample. It's not a core sample. That's being formed up in a little tube for testing. But that's also much like what you see as a concrete pier that goes underneath either a timber pier or a steel pier. If you've got deeply reactive soils, one way of getting around that, to still have isolated pier construction like this, is to just produce much longer piers. So you auger down deep into the soil. So when you've done your bore logs, you're looking at your soil, looking at, okay, it's reactive, not very reactive. Auger all the way down into that not very reactive. Form it up with plastic. Oh, there we have, yeah, do. So that's your vaporproof membrane that goes underneath your slab. If you form that up as a tube like this that sits inside your piers, you end up having slick sides to your piers, enabling that reactive soil to basically swell up and shrink without actually lifting your piers up, and the base of your piers can lock into that more stable soil at the bottom. So they'll detail the footing type, details the site works. So with reactive soils, we're thinking about moisture. What's happening with moisture? Where is that going? So it's about directing that moisture away from the building. There are requirements for having paving sloping away from buildings. So in high rainfall areas, you have to have 50 millimetres of slope over the first metre of your pavement. So your paving starts here at the edge of your building. By the time it gets 1 metre out, it has to be 50 millimetres lower. That's for high rainfall areas. So that's for areas that have a rainfall intensity of 125 or above. In Adelaide, our rainfall intensity is 124 millimetres. So we're just sneaking into that lower requirement of needing 25 millimetres of fall for your first metre. But with our reactive soils, it's very important that you do direct moisture away from the building. So any water that's coming down near the building, that's directed away. So typically with the slab design, engineers are also going to specify paving details for that property as well, to ensure that you have impervious paving, so either concrete pavers or concrete slab paving around the edge of your building, and that's going to slope away from your building to direct moisture away. Other ways that we deal with moisture are through ag drains. Has anybody seen that slotted ag drain stuff yet?
Yeah, I did a bit of brick paving, but also putting up retaining walls.
Yeah.
So when we have one of those retaining walls that you ever seen, at the bottom of where you excavated or dug out, where you can have the retaining wall, you can put ag pipe, which is like a plastic pipe, yeah?
Yeah.
It has holes all the way through it, but it still runs down, so that as the water drops into the pipe, it'll run away down to the road or somewhere else, and you're not coming back towards the house or the soil that will collapse the wall.
Yeah, exactly. Yeah, so I think they're called. Yeah, no, that's an excellent description. So it's a slotted pipe, flexible black pipe with lots of these slots in it. I'm fairly sure probably everybody would have seen some of it lying around at some point in time. That enables moisture that's in the soil or water that's in the soil to seep into that pipe and then run away. So it's put on an angle, and as you mentioned, it goes behind retaining walls. It's very important to get rid of moisture behind retaining walls for a couple of reasons. One reason is that you don't like that we don't like that unsightliness of water coming through retaining walls and depositing clay stains and things like that on the front of retaining walls. But also, when you add moisture behind a retaining wall, you vastly increase the load that's happening on that wall. As I said before, with the collapsible soils, when you add moisture to sands, deposited sands, they fit close together and they start to move. So hence you're increasing the load behind your wall. But the same with clays as well. So a lot of our really firm clays that we have here retain a lot of structure when they're dry. A fairly dry clay, you can cut almost vertically into that and it will sit there. But then you have a high rainfall event and that clay gets saturated, it wants to start flowing down. So if you're retaining a lot of moisture behind your retaining walls, that typically in Adelaide where we have a lot of firm clays, they start to get soft and they put a lot of weight on that retaining wall. So we have to deal with moisture. Well, it's very important to deal with moisture behind retaining walls, hence the ag drain and the ag drain and the aggregate that goes around it. So around that French drain or that ag drain, you pile lots of aggregate as well to allow moisture to seep through there into the drain. But we can also use such things like that around buildings as well. So to get rid of moisture around a building, you're not allowed to use an ag drain within 1 metre of a building because it can actually deposit moisture from one place along its length as well. So you have to keep them 1 metre away from buildings, but to ensure that you don't get terrestrial and sometimes subterranean water flows toward a building, you direct it away from that building with things like a subterranean ag drain. So engineers will detail things like that, and they'll also look at the trees and sometimes suggest removal of trees as well, or specify removal of trees to say, look, you can't have that tree this close to the building, well, not with the footing type that you've chosen to use. So you have to get rid of that tree as well. So they do that based on all the information that's in the bore log and the contour plan. So the contour plan, that tells us how steeply sloping that property is, but not only how steeply sloping it is, but where water will gather. So sometimes you get water flowing across land, but then it gathers in sections as well. So you really want to avoid places like that for building, because that's where you get a lot of variation in your moisture content from your soil. So they're going to look at all that and provide cut and fill information and that paving advice. So that's a soil sample that you're more likely to see on a mining site or a major development where you're going to be going down a long way. Typically our soil samples are around that sort of diameter. What's that, about 40 mil or so? So it happens from a push tube. Has anybody seen soil samples being done before? Yeah. Yeah. Oh, on your property. Yeah. What do they do it with?
It looks like just a big clunky pipe, like that sort of what it looks like, doesn't it? Sort of they just drill it down. Is that? Yeah. Sort of like you do in science as well. So kind of approach. Yeah. Yeah. So you basically just try and, I don't know how to describe it, but you just try and collect it and they just pull the pipe up.
Yeah, that's it. Yeah, but they have it on the back of a four-wheel drive ute.
Yeah. Yeah.
So it's a big setup, large hydraulic pump on the back of typically it's like going to be a Land Cruiser ute.
And they do it by hand as well, don't
they?
Because I've only seen it done by hand.
Right. Yeah. So how do they go about doing it by hand?
I'm pretty sure, unless I did the wrong thing, but I've just seen them sort of just going to the yard unless they've done something secondary to the first thing that they've done, and then they've literally just collected the soil just through like a big kind of tube, I guess. Does that sound right?
Typically for inaccessible, like for where you've got a lot of access, for where you can get a building, so where you can get a vehicle around. On a site, typically they'll do it with a small a fairly large four-wheel drive vehicle, and have this hydraulic drive on the back of that vehicle that has a stainless steel tube about 50 mil in diameter on the outside, but then it's only probably about 40 mil on the inside, and they've got and they're threaded sections, so they can join lots of sections together, and then that hydraulic drive at the back of the vehicle will provide a lot of pressure, pushing it down, but also turn it as it's pushing it down, and so it's going to push this large stainless steel tube straight down into the earth. And so they push down, 1200 mil or metre or something like that, and then lift it up, join another pipe on there, push that down, join another one on, keep pushing that down until they're about 4 metres down in the ground. They've put this big steel tube 4 metres down in the ground, and then they'll do the reverse of that. So they'll start pulling it up with that same machine, and then take off each section of pipe, and then with those sections of pipe get these boxes with core flute dividers in them, and just tap on that steel tube, and it puts out a sample of soil like this. So it lays the soil out in the boxes, and those boxes can then go to the engineer. The engineer can look at it and go, okay, that's the lowest portion, that's the highest portion, this is where we've got, you know, the top of our ground, etc. And they look through all that soil, and they'll see different strata of soil. And they'll see sections, okay, this is a really heavy, sticky, dense clay. This is a dense clay where we've got particles of rock and sand in it, etc. And so they'll look through that. But for inaccessible areas, I've seen a soil sample done inside a hallway of a house with setting up or taking up all the floorboards in the hallway, of course, setting up a tripod, and then using a two-stroke motor with a rammer to ram that steel tube down into the ground. So you go bop, 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 and then join more sections on and ram it down into the ground, set the tripod up with like a block and tackle, and just pull that tube up and undo sections, etc. So,
and so I guess the prototype was actually a pool, like an in-ground cement pool and spar. So I'm pretty sure they did something by hand though.
Yeah, so they just had like a hand auger sort of going down, did they?
Yeah. So I mean, what would they normally do for a concrete pool? So this particular project had a spar and then a water channel and then a pool. And they definitely had a soil report done. And I'm pretty sure that's what I saw them doing.
Yeah.
But it was by hand because they can't access.
Yeah.
The access was tight.
Yeah.
How would they normally approach that?
Well,
because you obviously need to get your soil report done.
Yeah, the only way I've seen it done for like your inaccessible areas is with a two-stroke motor with a rammer on it. And I imagine with a lot of the soils around Adelaide, you probably wouldn't, like for a pool, you'd want to be going down around that 2.5 metres to see what's there. And I imagine I'd still be using the two-stroke motor to ram the tube in. But I've also just assessing sites out with an engineer. Also just done like a push test as well, where you've got a steel rod that pushes down into the ground, and you have a meter on that measures the resistance, how hard you have to push that steel rod down into the ground. So that's just for getting the surface conditions to see what sort of bearing capacity that soil has. Various different methods, but by and large, you're going to extract a column of soil like that, and that column of soil is going to directly represent all the different layers of earth down to around that 4 metres, because in Adelaide we get movement in soils down that deep. So that the movement in your soil, that's going to be expressed in Y values. So Y is the factor stated in the footing report, which represents expected soil movement. So your Y values are how much is that soil going to move from extreme to extreme. So from saturation through to drying, what can we expect? How much expansion of that soil can we expect? So and I can't remember what your Y values are for each of these sections, so I won't go stating them off the top of my head. But your extremely reactive, that's around 100 millimetres or so. So 100 mil of movement, expansion, contraction from saturation through to drying. But then your stables are around 20 millimetres. Yeah, these are 20 millimetres, 40 millimetres, 70 millimetres, something like that. So that's our bore log. Now, did we get up to this point last week? The bore logs, I don't think we did we? So after sampling the soil, that's what you get. Is there anybody in this room that can make sense of that bore log? Can you make sense of anything in that bore log?
It's a draft.
It's a draft, yeah.
Soil description.
Yeah. All right. Okay. Beyond. So, but looking at the numbers and bits and bobs there. What beyond it being a draft? What can we see in that bore log?
See strength.
Yeah, we've got some. Yeah, got some strength. have a look on the left-hand side, you see that it's 3 holes. You actually see how far down each particular part is. Yeah, yeah. So what's our depth for each of our 3 holes? 3 meters. Yeah. This is getting great. And what else? What else can we? Actually, I might just duck next door and make that. Ask if they can make that a little bit quieter.
That's what it was.
So we've identified we've got 3 boreholes happening in here, and then we've got 3 meters is our maximum depth. Anything else we can see in that table?
YS, total movement.
Yeah.
Total displacement, YS, 54 to 65.
Exactly, yeah, so we've got our Y values. So for each of our boreholes, we've got 54, 56, 65. Is that good? Is that bad? Does anybody know? Give an idea?
Soil strength can vary how much load on one square meter. YS? Yes?
Oh, the Y, well, the Y.
That's the strength?
No, that's the expected movement of the soil. So how much we can expect that to move. So looking at that, that's not too bad. So that's sort of your mid to high range for Adelaide. It's not too bad, and there's not a huge amount of spread. So I spoke earlier on about shear forces, where you've got 2 actions happening right next to each other. Here we've got 54, 56, and 65. That's not a huge spread in value. So they're not. If we get something like a Y value of 20 or 30, and then we've got a 65 here as well, we're probably going to have to invest more in the footings to resist something like that than we do for something like this, where we can expect a lot of the movement to be fairly much the same. So it's not just about our total Y values, but it's also about the spread of those as well, because damage that happens to buildings is happening from differential movement. So when you get movement happening in one place, but you don't have it happening in another place. So we've got that information. So we can see we've got our 3 holes, we've got the 3 meters deep, we've got our Y values here, which sort of upper middle range of movement or reactivity for Adelaide, and not such a bad spread. Any other information we can get from that table?
Is that like, for instance, 54 either way, or is that like from the lowest to the highest?
Yeah, lowest to the highest. Yeah, 54 mil.
What should be bad? If that's not bad, what should be bad?
Around 100 mil or so. Or plus. Yeah, so 100 mil, that's when you're getting into extremely reactive soils. And then beyond extremely reactive soils, the other classification, we've got a P-class soils, which are problem class soils, problematic, and you're probably aware of that with your... Yeah.
There's lots of mixed soils around,
Yeah.
So obviously the sand will blow in.
Yeah.
Just lots of older houses, so you might all find some stuff in there.
Car bodies. Yeah.
Is it total gas, but 2 of the sort of moisture that's going to help? The estimated input?
Actually, I don't know.
It's just a flat out guess, maybe that's millimeters of rain or water that may land on that place.
Yeah.
Total guess.
Yeah, and that's all I can do as well. I don't actually know.
Because right before it says moisture,
strength,
input, and average input. So rainfall and moisture.
And both of those estimated and averages are both exactly the same. Yeah, that may be. Yeah, look, I can only guess as well. I'd hate to say.
But I still don't understand YS. What is YS?
YS?
So the YS, that is the Y value of the soil. So the Y value of the soil, that expresses how much expansion and contraction we can expect from that soil. Yeah, from saturation through to drying out. Yeah. So the other things we can see from this soil, from this bore log, okay, where it was, Clarendon. So we see, oh yeah, it's Clarendon. Yeah, we're going to probably expect soils like that around Clarendon. We can also see what type of soil we've encountered, so in terms of a description, and then we've got these horizons here. We've got A, B, B1, B2, B3, B4. Now sometimes the horizons are expressed in A, B, C, D, E, F, etc. This one they've chosen to express it as, they'll have a different letter for this top bit, because that top bit is extremely different than the rest. But then they'll make subcategories for our horizon B. So we've got horizon B, then B1, B2, B3, and B4. So there are different horizons of soil. So if we were to look at that soil report in a diagrammatic fashion, it has something similar. What do we? 1,000. And then, a soil sample taken through that. So let's go 1, 2, 3, borehole 1, 2, and 3. So having a look at borehole 1, our horizon A is 400 mil deep, but we don't have any of B1 and B2, so it's straight like this. So we've got horizon B3, which is horizon B3, clay, brown, grey brown, mottled yellow, high plasticity, few pockets of variably weathered siltstone. So clay with bits and bobs in it. And then borehole number 2, we've got some horizon A, got some horizon B, but none of B1 and B2. So once again, and that's 350 deep for our horizon A, but then different sort of, as I say, different layers of soil happening through there throughout our site. So we can look at that bore log and we can see, okay, in this spot here we've got these layers of soils, in that spot there we've got these layers of soil, and then look from that to see what sort of total movement we've got, what sort of bearing capacity we've got happening on there. So our first layer horizon, can anybody think why we'd give that first one a very different description than the rest?
What the estimated out previously.
Yeah.
Because the types of soil.
What's that? Well, it is a different
soil.
type of soil. Yeah, but why would we have a very different type of soil on the top?
Sand, stone, clay.
Yeah. But we'll have a very different type of soil on top because it's got roots and things like that in it. It's got humus, all that organic matter, all the stuff that's good for growing stuff in. That's all going to be on the top. So we can see our topsoil. This is going to be 400 mil or 350 mil deep. So, and then after that, then we start just getting into straight out soil without a great deal of plant roots and humus and organic matter in it.
Is there any way of testing that, or how do you find out the temperature of the soil? Because obviously that can impact the slab. If you're looking at doing a concrete slab or concrete flooring. So, yeah. So what's the best way to go about that? Because the temperature of the soil and how variable it is impacts the comfort zone of the inside of the house.
Yeah, I don't know. That's not something I've looked at before. Yeah, doesn't it average out around 19 degrees?
Yeah, but it can obviously be quite variable depending on the soil type it is.
Yeah.
has an impact on the temperature and how that slab feels, sort of in working on it.
Yeah.
And then it's also determines whether or not it needs to get some cooling in there, some insulation.
Yeah. No. I guess you could use a thermometer and you just have to test it over time, because it's not just about the test of a soil temperature at a given time. Yeah, you'd have to. Yeah, possibly there's a state government department that has all that information. So at the Waite Institute near Urbray, there where they've got their soil science section, possibly they've got information on soil temperatures and mapping. That's probably a good place to start. So when you've assessed your soil and you think about doing the building, you think about the various different types of footings that you can do. So what your lowest element is going to be. By and large, the most common thing we see is the slab on ground. So that slab on ground, it provides a thermal flywheel to the house, so it provides a lot of thermal mass. Helps keep that building cool in summer and warm in winter. That helps regulate that temperature, so to get temperature swings. It also enables the whole of the building to work as one, so to float around on that reactive soil. But it's not always going to be our best choice. To do a slab on ground, you need level ground, or you need things to be flattened out, or you can do a stepped slab of course as well. You can have a higher floor and then step it down to another floor. It does get quite expensive. Once you start stepping outside the bounds of the normal slab, things start to get quite expensive. And so to save money, we also look at other footing systems. So it might be a thing like a pier and slab. So that's a car park, right? But that's a really good idea of what a pier and slab is. Because if I was to show you, well, that's a pier and slab, you go, well, where's the piers? So with this, we see this concrete slab, and then we see that supported by piers at various different locations. And we quite often do that with buildings as well, like a slab on the ground, like this one here, that has piers underneath it to help support it, to bypass problematic soils or something and go straight into soils that we know and soils that are reliable.
Could you use that, say, if you had the third or whole one section of it seemed like the soil is completely weakened, so you put, say, a pier underneath that section of the slab, like what the rest of it?
Yeah, exactly. Yeah, that is where you see it getting used a lot, where you've got, as I think I mentioned it last week, through some sections in the sort of, we're looking at northwest of Adelaide, from Bowden, Brompton through sort of toward Port Adelaide. You've got pockets in there where they excavated for clay. So to get clay out of the ground, so you've got the brickworks there, so for areas around that, they dug clay out of the ground. They just filled it up with just about anything. And so you can have a section that's all natural ground, and then a section next to that, which is a pit that has all been filled in. A way of bypassing all that fill material that may still keep compacting over time is to auger a hole right through that to lock into the natural ground underneath. But there's so many instances of areas being filled from various different things, or having as Lee mentioned earlier, having pockets where you've got sand and then clay, etc. So for those sandy sections that don't have much bearing capacity, you might need to bypass those. So you create your piers by using an auger that digs out a cylindrical section of soil, and then you drop in reinforcing cages like this. This one's a square one, but you drop in cylindrical ones into there, so our reinforcing, and then fill that up with concrete. And that's This one's been created above ground. So they've made formwork, they've formed up piers, cast those, and then cast a slab with lots of support for their formwork underneath this. But you can do exactly the same thing just using the ground as your formwork for creating your slab and your pier. Another way is pier and beam. So this one here is a bridge, but we can see clearly in there they've got piers and then they've got beams happening. So horizontal section that's transferring the load of that bridge to those, we've got 4 piers, 1, 2, 3, 4. So it's transferring the load onto that. And the load from our surface, that's being transferred onto those beams by these beams heading in another direction. So that's a bridge, but we use exactly the same concepts and technology for producing flooring, like elevated flooring through other materials. So we might produce something much like that, but from timber, where we have piers, you have what's called a bearer. So the bearer is what transfers the load to the piers, and then you have joists. So your joists running perpendicular to your bearer, either joined at the same plane as the bearer or sitting on top of the bearer, transferring the floor loads to that bearer, which transfers them to the piers. We can do that in concrete as well. We mentioned it last week, waffle pod slabs. So this is what a waffle pod slab would look like. If you were to dig it out from underneath and you look at it from underneath, that's what a waffle pod slab would look like. Does everybody remember waffle pod slabs from last week? Everybody was, yeah. What's that?
I don't know what's here, but I don't know.
Yeah.
Pod slabs.
What's that?
Pod slabs.
Yeah. So where you got void formers, where you got things that stop concrete going in there. So you have all these squares set out. That's because we don't need to have concrete everywhere. We can increase the strength of something by increasing its depth. Hence, where we have these beams, we make how does that? So if we increase the depth of something, we increase its strength. So we want to be doing that. We want to make things deep. But if we make this whole slab like that, 400 millimeters deep, that's a lot of concrete in there. So to achieve that depth, but not use all of that concrete, you just put out spaces to say we don't want concrete in this bit, this bit, this bit, and you set up a grid. So you still have the depth of profile, but without the same volume of materials used for that. So that's same. So exactly the same principle. Yes.
Do they still with like a waffle pod slab have to dig excavation sort of footings, or is it just straight on flat ground?
It's straight on flat ground. Now it's although you're still going to have to dig stuff away. So typically your 400 mil of soil, that top bit there, it's got all the humus and everything in it, you have to scrape that away. And then your waffle pods, yeah.
When it comes to the concrete slabs, if say for some reason money was not an option or resources weren't an option, and you were to decide, you know what, I want to make a slab, and I want to make it a solid slab the entire way along, as opposed to doing this waffle pod.
Yeah.
Would that be stronger or actually weaker?
It'd be stronger. Yeah. But you're still going to get some strength by having all those sections filled in. But let's say we had a solid slab which is 400 mil thick, or a slab that was 100 mil thick with 300 deep beams on it. That solid one is still going to be stronger in the main than something with the beams. But for the amount of concrete, for the amount of expense, it's not going to be that much stronger. So
it's not a cost-effective strength.
It's not a cost. Yes. So to make things more cost-effective, you remove material from one portion and then add it to create depth of profile, rather than just using it straight through. But let's say we had a cubic meter of concrete. We have a defined given amount of concrete that we have to work with. If we made that cubic meter of concrete 200 mils thick, we'll get 5 square meters out of it, and we'll get a certain strength out of it. Whereas if we decided to make it 100 mil thick in sections, but 300 mils deeper for our beams, that same cubic meter of concrete, we can make a larger footprint from it, but be the same strength. So it's about the efficient use of materials, and that is super important in building, because efficiency makes you cost competitive. You have to be cost competitive. People do. Obviously, your clients are concerned about these things. Now, yes, you can have people that will have big budgets, and they will want to produce something amazing, something magical, and cost is not such a driver. But still you need to be efficient for other reasons. Other reasons you need to be efficient is for your impact on the environment. You don't want to be ploughing a whole lot of resources and energy, etc., like finite resources, into something which isn't needed. So to articulate the underside of our slabs to form slabs with beams, etc., we're making the use of those materials far more efficient. A footing system which isn't shown on here is the grillage raft. So a grillage raft is much like your normal raft slab, except its beams are really deep. So once again, that's taking that efficiency to the next step, to create even deeper profile of slab with less concrete. And then another footing type is strip footings. I think I mentioned this last week in context of talking about areas like Unley and Parkside. If you look at a soil map of Unley, they're not too bad, really. It's not the worst sort of soil you've got around there, but then you've got a lot of cracking happening in buildings because those old buildings were built on strip footings. So that's where you just have a strip, and unfortunately that strip of footing has to work independently than the rest because it's not tied together with a slab on the top. So it's not sharing its loads with everything else, and because it's working independently, it's taking a lot more stress just by itself when you have imposed loads, and you can get it.
So most houses are strip footing.
What's that?
Most houses are.
No, so I'd say most houses now are concrete slabs, but for the early days of Adelaide's development, it was all strip footings.
Oh, what it is.
Yeah, so when we started using concrete slabs in around the 1960s.
What are these days? What kind of slab is this?
Oh, raft slab.
Raft
Yeah,
slab.
90% of what gets built. So it's slab on ground, typically referred to as a raft slab, and it's stiffened with integral beams and edge beams. You remove the top layer of soil. You bench it, and sorry, we'll get into the waffle pods a bit more with that question. Yeah. So remove the topsoil that has all the compressible organic matter in it, and then you fill it. So because if we go removing that soil, we don't want to start building our house in a depression or a pit, because that's going to gather water. When water flows off anywhere, water flows downhill. You don't want to be building your house in a pit. So you have to get rid of that topsoil, which is too compressive for imposing loads upon. But then you have to bring in other soil that can be compacted to produce a stable footing for the building. So here we've got a site which has been benched, and then that soil has been brought in. So typically it's going to be quarry rubble, and it's compacted by wetting and rolling in 150 mil layers. And then your top bit, you use a bit of quarry sand on the top of that, or crusher fines on the top of that, both to protect this plastic stuff, and also just form a really nice top for cutting out your beams like this. So this section there, that's quarry sand. So quarry sand, dolomite, crusher fines, same thing, 3 different names. So that's on a fairly clayey sort of loam on top, but you end up forming nice beams. The real benefit in forming really nice edges and things like that is it's much easier to estimate your quantities of concrete required than if you've got a scenario like this where your beams, where the sides have crumbled and so on. So for that sort of thing, you probably want to add another 10-15% of your concrete on top, which, you know, if your concrete cost is around $10,000, you know, extra 10%, that's $1,000 extra. So it can be well worth bringing in some sand to form nice edges. You have to set your service pipes in. So you excavate for the beams and excavate for your service pipes, and then fill it all in as neatly as you possibly can. So once again, form very neat trenches to get your concrete required down, and then you have to lag those pipes. The reason you have to lag those pipes is because these pipes, yes, this soil's been excavated and brought back in, tipped back on, but that soil will over time get hard and will form around those pipes. If you've got a raft slab which is moving around like this on your soil, as it's meant to do, carries the load of the building, those pipes aren't necessarily going to be moving the same as the rest of that building. You're going to get some differential movement. To enable that differential movement, you have this spongy rubber wrapped around your pipes. So there's a section about this thick that doesn't have concrete. So the pipe doesn't have concrete around it, so that can move around a little bit inside there, because one of the things you really don't want to have are cracked pipes underneath the slab. Because once you get cracked pipes underneath the slab, you get moisture, you get more swelling, you get exacerbation of that issue, and then your pipe gets cracked worse, and it's very difficult to repair a pipe underneath the slab. You can sleeve them and things like that, but it's not much fun. Sometimes you've just got to cut through the slab and jackhammer away that concrete, repair that pipe, and then you've got a compromised slab. But the way you deal with that is you drill into the sides of your slab, you reinstate steel mesh, and you chem set that mesh into the rest of the slab, and then you pour back over again. So your steelwork is locked back into that slab. It's really quite a process. It's much better if you get this right to begin with. You know, costs hardly anything.
So what happens to the pipe that's gone through the ground? Do you lag that as well, or is it just?
No, so not yet. So it's just.
If it doesn't crush it at all, just sort of wait for the house and concrete.
No, because those forces are evenly distributed across the whole of the ground, and a lot of the forces are actually transferred to the sole of your beams. So that's, yeah. And for the purposes of specifying and designing slabs, it's about that sole surface on your beam and how that's impacting on the soil. Okay. But yeah, your lagging detail is important, and I would take issue with seeing something like that on site, because what we've got happening here, yes, that pipe is lagged, and that's lagged fairly well to that side there, but here we've got to get concrete right around that section there. So there's essentially that lagging isn't really doing much if the edge of our pipe is so exposed, and that's going to get all covered by concrete there. It's not going to allow much movement. So tiny little details like that can be very important. And also another thing that's, I've seen some shockers on sites, people putting in the steelwork for people putting in the steelwork for your slabs. Yeah, they work fast, they work hard, they'll move like several ton worth of steel and install several ton worth of steel in about 4 or 5 hours. You know, they're going flat out, and they, you know, to be cost competitive, they do that. But in that process, they're walking over all of this stuff as well. And you see pipes bending like this, and you think, do we have any cracks opening up in these pipes in that stage? Because it is incredibly important to protect your pipes underneath your slab. Also, at this point, to protect the building, you might want to put down like a termite spray, or I think I've got some here. Yeah, I'll pass around this. Yeah, I dare say this one doesn't have any termite poison in it. So you've got plastic membrane that goes down, and rather than just dosing the soil with stuff to kill termites, there's a thing like that which provides a plastic membrane, but it has the termite poison inside 2 layers of that plastic membrane. So if the termites try to eat through it, then they hit the poison. But if they're not eating through it, then it's not going into the soil. Or you've got things like this bit of Termimesh, which is pretty low tech, but yeah.
Chris, I can remember when I was a very young fellow doing builders labouring up north, Darwin, so they've got the Caulfield best blocks, rare down and stuff. And
yeah.
I was cementing in what they called mole strips.
Mold strips?
Mower.
Mower
Strips, like mold strips. They're around like 1,500. About that wide.
Yeah.
150.
Yeah.
Maybe, or maybe 300.
Yeah.
But the guy that came around before we made him said, nah, they're actually termite strips, because this substance has been banned everywhere else in the world. I look pretty good for a 20-year-old, but I had a laugh. I was about 45. Spraying that. Here's me working, cementing all these mold strips through the outside. That's to actually cover up the spray.
Yeah, right. Yeah. No, there's
problems up there. They're pretty.
Yeah. So you've got very severe termites for the North Australia, but still we've got plenty of termite damage happening down here.
I didn't understand it with that building. You wouldn't think there'd be much material that would be very edible other than cement.
What the building you're building with the Caulfield best blocks? Yeah, but it's okay. You look at a building, look at a building like this. Yeah, there's not much for termites to eat. Okay, there's some hardwood battens out there. Probably not even going to eat that anyhow. But your standard sort of house has things like timber architraves, and termites can even eat the paper on your gyprock. Not that that's a particularly common thing, but there's lots of little timber bits and pieces around your house, or your cabinets and things like that. Even your grand piano, you don't want termites eating those things. So if we look at the NCC, it tells us that we have to protect against the primary building elements of the building. So if it's a steel framed house that doesn't have any other edible primary elements, then we don't have to protect against termites. But it's really quite a good thing to get your termite protection in there anyhow, because there's going to be other timber elements inside the building that termites will want to eat. So, yeah.
So let's say you're building a house and you know 100% for a fact at this point in time, as you're putting in the slabs, there's no termite food anywhere in this house.
Yeah.
Later down the line, the person comes along. You know what? Actually, I want to change something in design.
Mm-hmm.
And now suddenly you've got termite food in your building.
Yeah.
And you didn't put any termite protection in.
Yeah.
And that probably have some trouble then, right?
Definitely. At that point in time, it's probably going to be a thing of saying to your client, look, that ship has sailed. We can't change our design now at this point in time because we don't have any termite protection. If you want to have those exposed timber portal frames or whatever you got, as your new idea, I'm sorry. So that's probably what's going to have to happen. You say, look, we don't have any termite protection. Because that happens at this stage. You're either dosing the soil with termite poison, or you're laying down a barrier that has the termite poison in it, or you go installing Termimesh, things like that. As a retrospective, you can get people that come around and drill holes around the house and put termite poison in there. But look, that's a very complex question. Maybe I shouldn't really broach that, but I would definitely be steering away from any retrofit sort of termite solution. Yeah, so in that situation, it'd be more like, well, no, that ship sailed, we can't go down that path. Yeah, but I think it's good to get termite protection in your house, anyhow. Even if your primary building elements aren't or edible. So you've possibly done termite spray and installed your pipes and done all your beams. Next thing to do is install all the plastic, so that vapor-proof membrane. This stuff here, I'll pass that around. If you want to see that. So you install that.
Special plastic or just normal plastic? Which you can buy at Bunnings.
Oh, you can buy it at Bunnings, of course. Although it'd be much cheaper to buy it at a construction supplier. So.
Just plain plastic, yeah.
Yeah, but it's not. So plastic, there's all different types of plastic. That plastic is actually really quite strong, and it has to be quite strong. You don't want that tearing and breaking, etc. It's try to pull it apart if you want it.
So you can stretch.
What's that?
So it doesn't want to stretch for a lot.
Yeah, it has a little bit of stretch in it, but it's
tight.
It's fairly strong, and it needs to be. So that provides an impervious barrier to the underside of your house to stop water coming through, to stop moisture coming up. And then wherever you've got overlaps, or wherever you've got sheet joints, you have to lap it by 200 millimeters and then tape it as well.
But how about the termite sheet? It will be below this sheet or termite?
Oh, termite? No, so that termite, that cordon barrier that I passed around, that you can use instead of this.
No, if we are going for this sheet,
Yes.
there we will be putting that termite sheet.
Right, so if you go for this sort of sheet, you can protect your termite, you can protect your house from termites by using mesh around all your pipework, or you can protect your house by spraying termite poison into the soil for that.
So in case we are going for this sheet, this termite sheet will not be required. That's what I would understand.
Yeah, so if you're using just that sheet, yes, then you need a different type of termite protection required. And other termite protection is things like crushed granite. So tiny little bits of crushed granite, termites don't like to burrow through that. But of course, you've got to be fairly thorough with the application of that as well. Another way, it's not termite treatment, but you can build all with steel or hardwoods or something like that as well. So after that plastic has gone down, then you fix all your steel work in. So our slab details will include the size of our bars. Now this is just an example. So typically your slab beams would have larger reinforcements. These are 8mm rods, are they? Or 10, probably 10mm rods. These ones here, deformed bars. So this is exactly what your bars would look like in terms of having all these little lumps on them. And then these are your ligatures, probably 6mm ligatures. Typically you got 8mm ligatures. So the ligatures is a thick, strong steel wire that holds all your reinforcing in place. Pass that around here to have a look at, and then you've got your tie wire on that. This one here is more your typical slab your slab detail that you see for your steel fixing. Probably got 10 or 12mm bars in there. We've got 3 on the bottom, 3 on the top, and then fairly long ligatures there holding it all together. Then on top of your steel for your bars, you've got this mesh which is included. Now that one's got 2 layers of mesh happening there. That's not so normal that you have 2 layers of mesh happening. But that mesh, that's to control the expansion and contraction of your slab. It certainly provides strength in the top of your slab against deflection, against bending, but typically it controls any cracking that happens in your slab. And that mesh is set up off the bottom side of the slab by these bar chairs. So this slab here has 2 different size bar chairs. So there's a large and a small bar chair passed around. and have a look at
So
it.
we'd use that if you had 2 layers of it. So you have one lower and one above.
One lower, one higher. Yeah. So that's not a typical detail. Typically, your slab mesh is happening at the top. So set 25 millimeters down from the top of your slab. This one, there's 2 layers of slab mesh. So one slab mesh on the bottom, one slab mesh at the top. Possibly they're building on some uncontrolled fill or something in that they need greater strength within their slab section, not within the beams.
Is that it's like on the side where there's none of the plastic, is that just a strip footing section for like the...
Yeah. So that's external. So outside the building, you don't need to have plastic. So you have to protect the inside of your building from moisture egress in, but outside you don't. So that strip footing, that might be for a veranda or something. Yeah, deck, something like that.
So you don't need it on fresco?
No.
Outside?
No. You might want to still include it in your alfresco, because if you don't, what happens is you get moisture coming through your concrete, and then that moisture brings in salts, dissolvable salts with it. They get deposited on the top as that moisture comes through and it dries out.
And can I take the grout as well, like the tiles and things like that? Start to,
Probably,
I
yeah.
just noticed outside that's starting to happen.
Yeah.
I was trying to work out why.
It may be dissolved salts. So what happens is when salts are in solution, they can be carried through. They can pass through things like concrete. But then as that water dries away, those salts are left there. Those salts are polar molecules. They want to form a lattice. They want to form a shape. And so those salts will be between the bits of grains of sand and so on in your grout or your mortar or something like that. And then they start forming their little diamond shapes and wedging things apart. Yeah.
With those chairs that are going around,
Yeah.
I noticed that they've got 2 different depths on them.
Yeah.
So it's like it sits in one way, it goes down to a certain height, but if you take it out, turn it around a little bit, it sits at a different height.
Yeah, exactly. Yeah. Because, yeah.
Also, I guess the slab's a lot thicker than when I was brick paving as well. The method that I was using is a bit different to most. We use quarry rubble and sand and both for whack to a point where it was like cement, so before you put the paints down.
Yeah.
By using quarry rubble and quarry sand, we found that after they were laid, at least for a little while, maybe 1 or 2 times, salt damp would come up through those particular materials through the pavers.
Yeah.
A very strong way to lay them, but you'd have to clean the salt damp off a couple of times after that would not happen again.
Yeah.
I don't have to do slabbers, but you were saying they use quarry rubble and quarry sand. Normally they use that orange sand nowadays and they just run it loose and whack it afterwards.
Yeah, it all depends on your quarry that you're getting from, what the supply is and what the dissolved salts are
Oh,
in,
okay. So you have to be
in
careful
that
about that.
location. Well, if you're using plastic underneath, don't be careful
Yeah, so
about that.
I was just going to stop coming through that.
Yeah.
Sorry.
No, that's okay. No, these are all great questions. And Tom, your question about the different heights of the thing. So like on this bar chair, we've got this one set here, and then we've got another little thing going through there. Yes, that enables the different heights of your mesh, and so these get set out really quickly. So you get guys just walking along, going pop, 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 dropping them in really quickly. So everything, that's the idea on a site, is that stuff happens really quickly. You're not going to have somebody go around and put something in, measure it, is that 25, it's 26, all right, let's get it done. You don't have that happening. But this enables you to get that accurate measurement of the height of that steelwork, again, away from the edge, in a fraction of a second. So it's like, boom, that's 25 mil there, or at that height, we're at 40 mil. So you've got different heights of things for you. That's all right. So you've got different heights of things on your chairs that enable that adjustment to happen.
Everyone checks the height of the soil. So is that the easiest role? So obviously, in order for that to work effectively, the soil needs to be at the exact height.
Yeah.
It needs to be at. So how do you check that?
Well, you can check that with a laser level. So
okay, so they'll just do that. Whose responsibility is that normally?
That's the people working on this. So you have contractors for doing the site works. It's their responsibility for it. But the people who are also laying all this, doing all your form work, etc., they should also be checking that. So those sorts of things should be checked several times. And yeah, and they might want to come along with a concrete rake, which is a big flat thing, and just smooth off sections to get stuff right.
So I imagine twice cut blocks.
Yeah. We'll have several different trades that rely on, or checking the work of other trades as they move through. So we've pretty much covered all that in our discussion. One thing we didn't cover is concrete coverage. So this steel has to be protected from the atmosphere. We can't just have steel right by the edge, because if it is right by the edge, then it can corrode. And the funny thing with this building, I'll give you the challenge of looking at the concrete as you're wandering around here. There are sections in this building, I'm not going to tell you exactly where. There are sections where the concrete has been ground down so you can start to see some of that slab mesh. Has anybody noticed that already?
I've only noticed like rods that were like necessarily going vertically, not horizontally.
Well, I haven't seen those. Yeah. But no, there's sections here you can see some of this slab mesh. So the concrete in some pits was poured at the wrong level. To compensate for that, it was just cut down a lot. That's not really a practice I'd be happy with. But I guess the engineers that were overseeing this whole thing, they could understand. Okay, we have this. Are able to sign off on that. And by no means is this building unsafe, right? It's it is. I wasn't saying that, but you'll notice that around. You have to provide that coverage to your steelwork to ensure that it's thoroughly protected. Now this is just cored through a floor. So we've got some terrazzo on top, which is another concrete product. It's got marble flex in it. That's a topping on top of a piece of concrete, and then we can see our slab mesh bits here like that. That has to have, I'll pass that around. That has to have minimum 25 millimeters of coverage to a protected area, or to the underside of the slab, it has to have minimum 40 millimeters of coverage. Also, and your slab mesh, it's also called fabric. So typically it's called fabric. I don't know why we have that term, but that fabric or that welded mesh or slab mesh has to be lapped several squares as well. Because if you just lap it just one square like this, when the people are setting it all out, or when your concreters are working on top, it does this, bends around everywhere. So you have to lap it several squares to provide that strength for working on top. So you can get your termite protection in place. So a stainless steel mesh is one option. The reason you have this stainless steel mesh sort of skirt around your pipes is because when concrete goes off, it loses moisture and it shrinks. And it shrinks away from your pipe. So you have several millimeters of gap between your concrete and your pipe, and that's a place that termites can get in. So you want to have that stainless steel mesh there to stop the termites getting in. So these little deformed bars here, that's your slab mesh that you can see there, and that's those little bits of steel you see coming through in that core of concrete. So here we've got the steel work for several different slabs. You've seen this one already. This one here, it's got that's looking at that straight away, you'd say that's a fairly reactive site. We've got 16 mil bars, 3 16 mil bars at the top, or a fairly heavy building, reactive site, heavy building, maybe a combination of both, and then fairly large bars there. We've got a very deep rebate happening on that slab as well, so possibly that's the heap of construction. Some more things happening here, so that's the same slab as our other one, so we've got 2 layers of mesh happening. So two different heights of chairs. You see your little short chairs and your tall chairs to set those heights exactly. So concrete is actually very cheap building material. It costs $300 a cubic metre typically, which is, you know, if you can go comparing that, well, can't even think off the top of my head what a cubic metre of steel would cost, but it's, you know, it's quite, you know, way more expensive than that. But your cubic metres of timber, you're sort of, I don't know, around $800 a cubic metre for your cheaper stuff, up to about $2,000 or so for your hardwoods, or actually possibly more for a lot of your hardwoods. So in the scheme of things, concrete is really quite cheap, the actual material, but there is expense that goes into the work. So we can't just put concrete there, we have to get everything in place. And one of those things we've got to get in place is our formwork. So with a residential slab, all these timber forms that can get reused. So that's going to get used on another one, it keeps getting reused. But on some commercial projects where you're doing interesting stuff, some of that formwork can't really be used, or it's, you know, it has to be made specifically for that job. Or for high-end finish sort of work, you really need to use new formwork. Yes, this room doesn't have any exposed concrete in it. If we look out the window there, we see that lift shaft. That's not really high quality concrete forming there in terms of they've recycled their sheets of formwork. So your formwork gets banged around, it gets nail holes in it and all that sort of stuff over time. If you're reusing your sheets, you end up getting marks and things like that happening, and funny edges happening on it. But I think there are some sections of concrete around in this building that are finished really nicely. It's a bit more high end. That's where you're using brand new sheets of form ply. You silicone all the joins to get all those joins really flush. You get really smooth surfaces. So that formwork can be a major part of the cost of the build. This sort of formwork, yes, it gets reused, but there's still a lot of work that goes into putting it in. So we've got lots of steel pins happening there, and all of our struts holding that formwork in place. It is incredibly important that the formwork is constructed properly, because if that formwork isn't constructed properly, on site, if you get a blowout of concrete, yes, it wastes concrete. It means you're going to have people diverted from their jobs to fixing that formwork and getting that formwork to happen on site. But it also means that you've lost this section of concrete, and you might end up being short of concrete for the rest of the slab. And that is that's really not a very good situation. So you might have to get a mini mix in or something like that for some extra concrete. So it's imperative that your formwork is constructed properly and can take the loads of that concrete. Another thing that engineers are going to specify is the lifts. The concrete, if you're pouring something which is really tall, that concrete, being in a sort of plastic or liquid form, has head pressure. So if you think about water and, you know, supply of water, if water is up high and it goes to a low point, it provides a lot of pressure in there. If you've got a tank right up on top of a hill, you get a lot of pressure in your pipe down the bottom. That's head pressure. So that's the distance away from the top of that material through to the outlet. Same sort of deal with concrete as well. If you go pouring lots of concrete into a very tall form, then there's a lot of pressure at the base that can pop it out. And so it's not only important to think about the design and the structure of that formwork, but also about what height of concrete you've got to be laying in each section before it starts to go off and solidify. That concrete, by and large, happens by a concrete pump. Yeah, one thing you still see it on sites, barrows, like wheelbarrows, but that's not how the majority of concrete ends up being placed. You have wheelbarrows on site for placing small amounts of concrete, etc. By and large, a concrete pump will put the concrete in place. Yes, it is expensive to hire a concrete pump, like sort of that $500 a day or so, but it means that the whole slab pour happens much quicker and much easier. You don't have people barrowing concrete in place. So this thing here, by the way, is a concrete pump. Sorry, and that's the concrete coming out of the nozzle. And we've got our concrete truck pouring straight into the hopper on the back of the concrete pump to put that onto where we need it. So at that point in time, before you go pouring concrete in there, you're going to have given council 1 day's notice, and same with the engineer. You've got to let the engineer know that concrete pour is happening. That concrete has to be put in place, and it has to be screeded, and it also has to be vibrated down to fill up all the little gaps and things. Well, drop bits of concrete over here. Send that bit around. That one is actually not. That one's called a bony mix. That's where you just don't have enough sand or fine aggregates in the mix. But you also get that exact same effect if you don't vibrate the concrete down enough. You get all these air pockets in there. And with those air pockets, obviously you have significantly reduced strength. So if we've got some sections in there where the concrete hasn't been all vibrated down to remove all of that air, we just get sections where it's weak. And as you know, something is only ever as strong as its weakest link or its weakest section. So concrete has to be thoroughly vibrated down into the formwork. There's several ways of doing that. One is with, do we have any pictures of people with vibrate? No, I don't. So don't have any pictures showing that. But your typical concrete vibrators, there's a two-stroke engine that's going on someone's back, and they've got this large flexible piece coming off that and a rod that just shakes around like crazy, and they plunge that rod in with the concrete when it's all placed to settle it all down and to move it all down and get all those air bubbles out. That's one way of doing it. If we were forming up that lift shaft like that, we wouldn't do it with a rod, a vibrating rod. The way we'd do it is by placing these vibrating units on the side of the formwork. So you've got this formwork and this little unit that pops on the side, and that sends a shake, like a very fast, minute shake through the whole of the formwork and makes everything settle down. But if you're doing strip footings and things like that, another thing you end up doing is you go banging your formwork as you go working along as well. That settles all that concrete around your edges and settles it all into all these corners. There like that.
I've also heard of the slump test with the cone, because sometimes council won't come out that day.
Yeah.
And in advance when they don't come out, which is a good thing, because normally when you're laying whole slabs, as I've heard from a cementer, he said the other guys on the site so gutless now to do it. I'll just put a hose in the back of the truck to keep it. So by the time the concrete gets there, by the time it's all poured, so it needs to be wet in between there if you're going to keep the consistency the same, which is actually illegal, I've heard now.
Yeah, you know, what
you're allowed to add water to the cement, that's what I've heard.
Oh, definitely. Yeah, what you've done is in your statement you've exposed. That is a real issue. So your strength in concrete comes primarily from your cement-water ratio. So if you've got weak aggregate, so whatever's the weakest link is going to fail. If you're with the stones in your concrete, that aggregate, the coarse aggregate, if that's really weak, well, that's going to break. So you need really strong aggregate. Then you also need really clean sand to bind well with the cement, because if you've got clay in there, it diminishes the binding. If you've got those things right, if you've got clean sand, strong aggregate, then the strength of your concrete comes from the cement-water ratio. If we put more cement in, well then that concrete is going to be stronger. Or if we put less water in, that concrete is going to be stronger. But the thing is, if we put less water in, then the concrete's not very, very workable. That's fairly high slump concrete. We can see that by the way it's pouring in there. It's very liquid. And what we're talking about when we talk about slump is we'll have a cone, fill that cone up with concrete, tip it down like that, and lift it up, and it goes out like this. It pours out flat. That's really high slump. It's slumped a lot. if we lift up that cone and it stays there in that's very low slump. Low slump concrete is very hard to work. It's hard to get it into all your forms. And if I'm forming up a lift shaft like that, I'm not going to be using low slump concrete. That's going to be high slump concrete because I'm pouring it down long distance. I want it to settle in there. And when we pull away that formwork, we don't want to have, air pockets and everything exposed. We have to have very high slump concrete.
I was just sort of mentioning over the time of the form,
Yeah.
change. And so if you know what you're doing, technically you should be able to get that ratio right. But the longer it takes, the worse that ratio is going to get anyway. It's going to dry out.
Yeah.
So
Yeah.
they kind of need to add water to it, otherwise they're not going to get the whole job done before it dries out. Unless they're perfect, because there's also travel time for the truck as well.
Exactly,
Yes. I know, I'm just swearing at you because it's way against the rules.
No, it is way against the rules because when you add water, yes, you make it weak, but then also if your concrete has started to go off, if that chemical reaction has happened, and then you're adding water and you're still agitating it, breaking it apart, you're not going to get anywhere near the same sort of bond. Obviously, so planning is incredibly important. Planning for a concrete job is incredibly important. And also keeping your suppliers, like your concrete suppliers, keeping them accountable for the product they supply is also,
So they supply the product. So when it comes in the truck, has the perfect ratio been created?
Yes.
As with the supplier?
Yes.
So no one should be touching that?
No one should be touching that. Unless that person touching that is an engineer or somebody who understands that concrete really well, and the person who has engineered that concrete will sign off that what they're doing is okay. So you've got various different admixtures you can add to concrete, things you can add to it to enable more slump to happen, to speed up the drying time, to slow the drying time, all these sorts of things. But basically, it all comes down to that planning. Certainly, what you do not want to have is a concrete truck stuck in traffic. If you've got that, because once concrete's all poured together, you've got water in there, it's starting to happen. So time, it's like cooking. Time is of the essence. Things have to be.
The guys that are laying it and the guys that are providing it, the guys that are driving it are accountable for the state that it gets through then.
Yeah.
So they'll be held responsible if that slump's incorrect.
Yeah.
Inconvenient, but if there was an engineer on site who realised that it was, it had gone off too much already before it got there, he's not going to have a go at cement, he's going to have a go at
the concrete supplier. And good. Yeah, and you have to hold your concrete suppliers accountable as well. Certainly, if you're partway through a pour, you don't want to be making those difficult decisions. You don't want to be sending trucks back. You don't want to say, look, that has gone off. You've been stuck in traffic for half an hour. Look, it's too solid. We won't be able to work it. Best case scenario is you don't want to be making those calls. If anything, you want to make that call right at the start. But with tens of thousands of dollars worth of concrete potentially in a truck, it's very important for those suppliers to get that right as well. And for some scenarios, it might be the best thing to have the concrete truck arrive with a water truck as well, or somewhere close by for that exact amount of water to be put into that concrete for making that as well. But Lee, you were about to say.
Oh yeah, I was just wanting to say too. I think that's really critically important when those concrete slabs actually with the concrete floor. It's really
yes,
that's it. So
yeah.
But I think the thing there's not that many concrete suppliers in South Australia in the Adelaide metropolitan area, so that is a real risk of it getting to site in okay condition. But then the other thing that I was wondering, so the average size house, say, is 200 square metres for the ground floor, the slab.
Yeah.
How much could you actually lay before it becomes an issue? Like, would you have to lay the slab in parts over a couple of days?
No, you don't want to do that. You want to,
house,
you want to.
As long as everything else goes
most definitely you want to do a continuous pour. The only situation where you're not doing a continuous pour is where you have really deep beams.
Okay.
So for those really deep beams, you cast lower section first, and you keep a rough top to that. So a top to that concrete that can easily be bound with the second layer of concrete. But except for that scenario, you always want it to be a continuous pour. So and also, so concreters start really early in the morning. They'll be on site at 6:30, 7 o'clock or something like that, or sometimes even earlier. Now, the EPA say that you're not allowed to go starting on site before 7:30 in the morning, and certainly if you've got a concrete pump going bonk, 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 bonk at 7 o'clock in the morning in a residential area, you're probably a really unpopular, or you will be a very unpopular person. But to get that concrete pour happening at that time of the morning is a fantastic thing, because your steel work is still cool. If your steel work heats up, it expands. And then if your steel work is hot when you put the concrete in, and then it cools down from that initial contact with the concrete and it shrinks, you don't get the same bond with the concrete and the steel that you want. So it's great to start really early in the morning for that reason. It's also great to start really early in the morning for the reason that the work is it's cooler, people can work flat out, and also you're not getting concrete trucks stuck in traffic because you're doing all your stuff before that. So it's quite often.
These guys will do it all their life. They told me that.
Yeah,
and it used to be illegal. They know, they have a fair idea that it's fixing the problem, not destroying. And
yeah.
I know it's not and it's not as designing your problem anyway, is it? The way that they laid, wouldn't the engineer that was supposed to be there?
You can write, okay, we've got 20 MPa or 32 MPa concrete, and you put that on your drawings, and it's like, this is what it is, and this is what it has to be. That's your problem. Yes, definitely. And then it comes down to the site manager who goes, no, that's not good, send it away. Yes, it's all, as a designer, it's not your...
And building insurance as well. For as far as time, not paying for the cement twice, if it starts the first time or removal or whatever, that's to fix it.
I think if
they
the
can do it in a long report.
Yeah, if the concrete's not rocking up as it's meant to be, well then that's on the supplier. So you're not going to be paying that bill. But yeah, of course, various case specific things. But as the designers, you have to understand these things. You have to understand essentially the concrete does have to happen as a continuous pour. If it's not happening as a continuous pour, then you have construction joints. Those construction joints are going to be articulation joints in the building, etc. And that has to be catered for throughout. But you also have to think about the practicalities. How are you going to get concrete to site? When you can be doing that? How that's all happening. So we've got our concrete there. We've got everything organised to the T. Things are going ahead properly. Concrete's getting placed. It's the right slump. It's the right mix, etc. We're getting it all vibrated down into the forms. The next thing we do is we screed it off. So screeding off, that can be so if you're doing a small strip footing like this, you'd screed that off with just a piece of timber across the top of your formwork. That's fine. And for some smaller slabs, you use a manual screed, which is an aluminium bar. It's got a handle on the top of it. Just move it like this, and you chop and you force aggregate down, etc. But for larger jobs, you use a vibrating screed that has a motor on the top of it, and that makes life easy. Just drag it across like this, and it sets all that concrete down in there. Then, so the way you think about concrete is it's about getting it smoother and smoother and smoother and smoother and smoother with every action you do. So you screed it, so you get it from lumps this big down to lumps about that big with your screed. Next thing is your bull float, so you get big flat steel float on a long pole, and you're moving it around like this on top of the slab, and you're getting it down to differences like several millimeters. So that's floating with the bull float, and then you trowel with your steel trowels to get it even smoother. Typically, you're not going to be doing it by hand. Yes, you can hand trowel concrete for sure, but typically you're going to be doing it with a motorized trowel. This is a smaller hand-operated trowel, and you end up troweling once that concrete has gone off. Once it's like 2 or 3 hours old and it starts to solidify. Now, you can As I said before, you can add different admixtures. You can make concrete go up fast, or you can make it slow. You can retard that setting time. So it might be a short amount of time or a long amount of time before you start trailing off. That also has to be considered in the whole planning of the job and thinking about when things are going to happen. But you get this motorised trail on there, and that forces all the aggregate down and produces a smooth surface. And then you've got your other ride-on machines like this. Those ride-on machines will get a really nice surface on the concrete, but obviously you're not going to use something like that for a residential slab. That's more for if you're doing a major, like a large project. Because you're going to have to, you can't just lift that off the trailer and put it on. You're going to have a telehandler or a crane or something on site for picking that up and getting that on concrete. So your concrete, or your slabs have set downs in them. It's very important that you set down the floor of your bathroom, because your bathroom, you want all your tiles to slope to the drain. Several options here. You can do a bathroom without a floor trap in it. So this pipe in the middle, this drain in the middle, that's our floor trap or our floor drain. You can do a floor without having a floor trap in it, but that means you have to have overflow protection on all of the things in your bathroom. So you've got to have this. If your hand basin fills up, you have this little hole in the back of it that goes into the pipe. Anyhow, your bath, etc., has to have that overflow protection. And any floor water, if you don't have a floor trap in there, has to flow back to your shower. So if you're doing a tiny bathroom like this, yes, you can get away without doing a floor trap. So because you can slope your whole bath or the bathroom area back to your shower. Your floors for bathrooms in South Australia, the main floor area has to have a slope of 1 is that 80. So for every 80 millimetres of distance, you've got to have 1 millimetre of fall. So over an 8 metre bathroom, you've got 100 millimetres of fall happening in there. You as designers, you have to think about that. You have to be aware of that. To think about. So for every 80 millimetres of distance, you've got to have 1 millimetre of fall. So that means for 800 millimetres of distance, you've got to have 10 millimetres of fall. For 8 metres, so 8,000 millimetres of distance, you have to have 100 millimetres of fall. So from highest point to lowest point. If you're doing a bathroom that's 4 metres, like this is a large bathroom, right? But if we've got 4 metres distance, and then you're planning to have your shower as your draining point, which is right in one corner, you've got 4 metres, you've got to have 50 millimetres of height difference from one side to the other. You need to know that for specifying how much to set your slab down, because that slab set down, that dictates how much screed you can then put in that floor to produce that slope. So when we pour the concrete slab, we don't produce the slope. That's something that has to happen very carefully. So what you do is you produce a set down, and then you get all those slopes in there later on with the concrete screed. So, a cement screed. And then you lay your tiles on top of that. So when it comes to specifying what your set down is, you need to think about how much height difference we need between our highest point and our lowest point. So that's that 1 in 80. So 1 in 80 for your general floor area, and for a shower it's 1 in 60. So within this shower area, you have to have a 1 in 60 slope. Also, there's a thing called puddle flange, which helps drain the moisture out of that cement screed as well. For a puddle flange, you need 20 millimetres of screed contacting with that puddle flange. So you have to add 20 millimetres to the height of your distance there as well. So if we had our 4 metre bathroom, we're planning on just having our shower as a drain for that, we need to have our 20 millimetres depth at our puddle flange. We have to have 50 millimetres of fall over that whole distance. That means we have to have 70 millimetres of set down just to produce that screed. Let's say we've got 6 millimetre tiles. On top of that, we're at 76 plus a little bit of tile adhesive underneath. We're probably going to have an 80 millimetre set down. we probably don't want to do an 80mm set down. The reason we wouldn't want to do that is I spoke earlier about concrete coverage, about your mesh and everything. If we're doing an 80mm set down in our bathroom, then all of our mesh in that section has to be down even further, and that requires a lot of detail with that slab. So it's often a much simpler, more reliable, easy option to have floor trap right in the middle, like that one there. Produce a separate set down for your shower where you have 1 in 60, and that will now enable you to get away with a much smaller a much lower set down for your bathroom. Does that make sense to everyone? So I don't expect you to understand set downs and bathroom design and things like that straight away. This is something you've got to learn over time, but in essence, that is something that has to be planned for initially. So when you're specifying your slab, you're thinking about your set downs, you're thinking about the slope relationships in your floor, where you're going to have a floor trap, if you're going to have a floor trap, etc. And that set down happens in your concrete by, you pour that section first, and then you put out some timber boards, stake it with some steel pins, etc. So it starts going off a bit, and then you build up your concrete higher around it. So it's not like you chop concrete out of there, you just pour that section first, your low section first, and then pour your high sections later. Then the concrete needs to cure. So it's not just about, you pour concrete and you walk away and you trail it off and so on, it's all good. You've got to take care of that concrete. If you slow down the drying time, or the time that your concrete goes off, you get stronger concrete. The reason for that is because, like any sort of polar molecule or chemical reaction that forms a lattice, like concrete, if you slow it down, then you get much better bonding happening with all your elements, and you get this stronger lattice type structure happening within your concrete. So you pour it, you get it all trailed off, you get the surface you want, and then you can spray on a covering that stops the moisture loss to that. So the underside, you've got plastic underneath there, you're not going to be losing moisture through that. The sides, if you've got nice, lovely, smooth form ply, you're not going to be losing a lot of moisture through that. But the top, you will be losing a lot of moisture through it. It'll all be evaporating. So curing concrete, slowing down that reaction to produce stronger concrete, is about slowing that moisture loss, primarily from the top of that concrete. So you can spray a cover over the top to stop the moisture being lost. You can cover the top of it with plastic, or you can have a really fine spray of water going across the top there all the time. Typically, your curing compound is going to be the most common thing that's done, because concreters can then spray that on there and they can knock off. They go home. There's no maintenance involved with that. Here's some details for you, showing a cross section through a stiffened raft slab. That shows set down for brickwork to ensure that any moisture that gets in there isn't going back to our timber. We'll talk about those sorts of things a little bit more later date. But you have a set down for your brickwork. You've got your mesh at the top, your expansion mesh, and 25mm coverage. That we've got all our steel bars in there, all held together with our ligatures. Does everybody understand? I'm fairly sure I explained this last week, why we put steel and concrete together. Everybody understands that thoroughly?
Prevents concrete from cracking.
Yeah. Steel's good in tension, concrete's good in compression. So some more concrete details for you, so to have a look at these things at home. Cross sections through slabs. This slab over here, this has got a starter bar in it. So that's because you were talking about Caulfield concrete blocks earlier on in your termite treatment. That's what you do for your Caulfield concrete blocks. So concrete blocks Caulfield and concrete blocks is a fantastic thing for building solid structures. What's that? Yeah, because you can transfer your uplift and you've got weight there. But you use core fill concrete blocks for underneath a veranda or something like that that's stepping in, where you're creating height difference from an elevated slab. So use that in buildings as well. So does everybody here in this room know what a Besser block is? Anybody who doesn't? Right, so yeah, Besser block's pretty ubiquitous. They're hollow in the middle. So you can set them, let's say you set them on a concrete slab like this. Before you go setting out when you're pouring your slab, you cast in some steel reinforcing in there, those bars, at every 300 millimeters or 600 millimeters, always increments of 150 millimeters, because that's where your spacing of your holes and Besser blocks are. But you cast your bars in there, and then later on you put your blocks out and you can fill that with concrete. And so that concrete bar ends up tying all of that brickwork to the slab through tension with the concrete bound around it. You can also build a retaining wall in that fashion. You have a foot going back, Besser blocks straight up, and then the weight of your soil goes against that foot to stop the rotation of the wall. But whenever you set your bars in, you don't just like poke them into the concrete, because that way you won't get much strength for pulling out. You put what's called a cog on the end, so you bend a section at the end to bind into the concrete.
No, actually, like if we do a hole in the base and then use the welding rod, because they go up the top and they core fill a bit, just use a little welding rod to make sure the cements go all the way down the bottom when they core fill it.
Yeah.
The hole.
Okay.
So
I'll just check. Yeah. If you're doing a lot of lifts of concrete, like high lifts of concrete,
yeah, just core filling. So
yeah.
Tops of that spot to make sure it's struck all the way to the bottom.
Yeah.
Otherwise it could be looking nice on the top and not actually going all the way down.
Yes.
Piece off and,
and there's no strength at the base. Yeah, where it's needed.
Excuse me.
Yeah.
Falling brick. Falling brick? I didn't you clearly about the falling brick or some.
Oh, the core-filled Besser blocks. Core-filled. Yeah. So core-filled. Yeah, no worries.
Oh, core-filled.
Yeah. The core-filled block work. So waffle pods, to answer your question earlier on, that happens on a flat level site. So you take out the soil with the humus, you bring in some other soil, but it's just flat. And then you put your plastic on top of that, set out your waffle pods like this. These are your styrofoam pods, and you have pod block spaces between them. These things that create exactly the right space between them, because all of these beams have to be their designed width and size. So you set out your pod block spaces. And those pod block spaces are also bar chairs. So I'll send that around. That specifies the height of your steelwork within your concrete as well. And then you set out normal bar chairs on top with your mesh there, that goes on there. So there's not a great deal of excavation that has to happen for your waffle pod. And then you set up formwork on the edge and you pour it. So much the same sort of sequence as with your.
Where is that waffle pod mostly used? Who uses it? Who put that waffle pod?
You're going to use that where you don't have really high Y values, or where you need to pick your soil up. So for Y values over 80, I think you can't use it. So for that bore log we saw for that place at Clarendon with our Y values of 54 to 65 or so, you could use a waffle pod for that. And the reason you use a waffle pod is because it's more efficient with your concrete and steel. To get your slab, you're using less concrete and steel, or about 30% less than you would with a standard residential slab.
We use it with my house because right in front of the house is the flood zone. I live near the river, so
Yeah.
56 floods is like right there, so we have to, so we use.
To pick it up, that 400 mil or so. Yeah. Yeah, and that's that's another scenario which you'd use it as well. Pier and slab. So I'll just move through these things fairly quickly. I don't want to labour on this too much. So pier and slab, you auger your piers out. You dig them into the ground. You drop your reinforcing into those piers, fill it all up with concrete, and then pour your slab on the top. Pier and beam, you'll auger your piers, and you may form up concrete beams like with like former tube or something like that, big tube for producing cylindrical columns or piers, or you may use timber piers or adjustable steel piers on the top, and then place your beams on top. So with your assignment, with that task 1 research assignment, you've got to compare several different flooring systems. So everybody's had a look at that one so far. So our first flooring system, our concrete raft slab. So we've covered that, we've looked at that, everybody understands what a concrete raft slab is, what it does, what its pros and cons are, although with some research and looking into things, you're going to understand those a great deal more. Next thing we're looking at are a suspended timber floor and suspended steel floor. With our suspended steel floor and our suspended timber floor, we're going to have a footing system like this, where we can't just, actually no, you can. You can actually just sort of auger holes, and then you ram posts in, so you can ram timber posts in. That's a possibility. You see that happening, you still see that happening with CCA treated timber. So CCA treated timber, that's copper, chrome, arsenic. It's that green timber. Does everybody know what CCA is? Seen it? No? I'll Google search it, because I'm fairly sure once I get an image happening with that, you go, oh yes, I know that stuff. What a typical picture of it. Well, that's fairly typical. I'm going to come up with CCA posts straight away. Look at that image. Has everybody seen that green pine? Stuff like that, used a lot for if you've ever been through a vineyard, you'll see lots of, so that's treated with copper, chrome, arsenic, so all of those things probably not particularly healthy, the latter, the worst. But, of course, termites don't want to eat it, right? It's going to, you put that in the soil, it's going to stay fairly well. So that's one approach. You can dig holes, you can ram posts in there to bypass some of your active soil, etc., pick your house up. That's one way of doing stumps. But for many scenarios, you're going to be looking at doing a concrete pads or concrete piers underneath your exposed piers above ground. So you're going to be looking at doing a scenario like this, where you have some soil removed, you fill that with concrete, and then you provide a level footing, a very strong footing to that pier, because concrete is very reliable. We can mix up concrete to be 20 MPa concrete or 32 MPa or 40 MPa concrete. We can say this is the megapascals bearing capacity of this concrete is. That can be fairly easily controlled and determined. Whereas, as long as they don't wet it down when it arrives at the site, it's going to be fairly reliable. But with dirt, with soil, things like that, it's going to be different for different bits. You're not just going to put your pier on top of that typically, and also you need something to tie it down into the soil. So wind likes to pick buildings up and lift them off. Now, obviously, there's a great deal of weight in your building, etc. You don't get that sort of that thing happening here, or not in South Australia. But wind does suck things up. We still need to tie things down to the ground. So one way of doing that is with concrete, and that's a very simple way of doing it. So for your elevated floors, pier and beams, both your timber and your steel flooring systems are going to rely somehow on piers and beams happening, and that's typically going to be onto concrete. Although, while we're on it, we're diverging a little bit, but I guess it's pretty handy for you. Has anybody seen anything called diamond piers before in your research? I'll Google that as well while we're digressing a little bit, because that is it's a concrete alternative. New one. It looks like a spacecraft or so. What it is, well, once again, it is a bit of concrete, right? But it's not a lot of concrete. So you got this little concrete thing which is precast, and it has holes which are heading in a direction, and then you can get sections of galv pipe with a post rammer and just drive those in at these defined angles, fix them and lock them so that diamond pier, it enables bearing on the soil, because you've got all these feet which are spread out through your soil, so that can transfer a lot of load to your soil, but then it also provides a lot of restraint against uplift, because you've got all your pipes down in the ground on this angle. If that was set in the ground and you try to pull that out of the ground, that's a very difficult thing to pull out of the ground. So that's one way of doing a footing system that locks your building into the soil without using much concrete. So a very small amount of concrete, but of course limitations, or can anybody think of any limitations with that? Space between piers? Yeah, you can rotate them around though. I think that you can plan something like that.
Probably don't take up that much room, and you'd have to space out your piers.
You would be, yeah. You do have like 2 metre space between your piers anyhow.
If you've got lots of existing pipe work or anything around, there's lots going on under there, you can't see it.
Yeah, that could definitely be a limitation, yeah, for sure.
Labour intensive.
Labour intensive, yeah, well, but not really. All your alternatives are quite labour intensive as well. Although where it would get really labour intensive is where you're ramming into soils that have a lot of rock and shale and things like that. And that's probably the biggest limitation that comes straight to mind, is you can't really ram these bits through stone. And if you've got a site which is sheet limestone about 200 mil down with a sandy top to it, no way you can use that. So you have to think about your site, and probably if you're building on sand, you probably wouldn't want to use those on sand either. While I'm having a lot of fun digressing, there's another footing system I think is probably good to show you. There's a screw pile. Has anybody heard of screw piles before? Yeah? Have you specified them on the job, or?
Yeah, I did it.
Yeah?
I designed it.
Oh, you designed screw piles. Right.
I'm not good at English.
Yes, no, that's fine. Yeah, sorry.
I don't know.
Yeah, no, I'd love to tap into that. But maybe that's probably good. The Chengguo, is that similar to what you've designed
Yeah.
before? Yeah, with multiple screw
Yeah. Yeah, I designed it about 38 meters. 38 meters.
38 meters deep.
Yeah.
Wow. What was that for?
Yeah, because in Shanghai, it's not good soil.
Yeah.
Yeah, in Shanghai.
Yeah.
Soil
Yeah.
is just really soft.
Yes.
I have to design goes down to the
Yeah. To the firmer soil, to lock into that.
yeah.
Yeah. Also to produce, bearing capacity, but also uplift. Yeah. Wow. So in South Australia, we don't do any screw piles anywhere near that sort of 38. No, we're not dealing with that sort of thing. In fact, even that is relatively crazy. Sort of well, that would be about 5-6 meters deep. So, but a screw pile, that's just a steel tube with some angled pieces on it, just like an auger, that screws down into the ground. And of course, by it screwing down into the ground like that locks into the ground really well. Another really cool thing is that you can put screw piles in like that. So you put them in with an excavator. So you've got an auger driver section on top of your excavator, and also I'll go into that later. But you can put screw piles down, put a building there, then decide, okay, let's take that building away, let's dismantle it, let's take everything away, and unscrew the piles and go without, basically not leaving a trace on the site. So fantastic for things like that. But also you can, it's fairly contentious. There's varying opinions about this, but you can also use screw piles and then lock them into a concrete slab as well. So your concrete slab can be locked into your earth. Problems with that are that it doesn't enable the slab to move like a raft, etc. But that is also specified by some engineers. Screw piles, slab, and lock it in place. So screw piles might be a really fantastic thing for an elevated floor as well. So once again, concrete-free alternative. Oh yeah, one thing I was going to say though, also with the installation of your screw piles, it can go fairly quick and easy as well. Because your auger just drives them down there, and it typically takes two people. You've got somebody in the excavator, and then somebody who's standing there with the screw pile, and they've got their spirit level, and they put it, okay, it's right, and they tell the excavator driver to move forward and backwards, whatever, to get that screw pile directly straight, start driving it, keep checking it, and then drive in. So that's the process in which it happens. So pier and beam, that's what's going to be used for an elevated floor system. So for timber, you end up having your piers. Now they might be concrete piers, they might be screw piles, they might be diamond piers, there might be all sorts of different piers. You might end up having brick piers above the ground. So brick's a very common material. You might form up concrete piers, or you might use adjustable steel piers. So everybody's seen adjustable steel piers. That's key. Do some Googling on that, some searching on that. Good to get that one bigger. Right. Close that one down. That's a larger image. No, it's tiny. Can everybody see that clearly enough? Maybe that's better. Yeah, okay. That's quite good. So what we can see happening in this picture is we've got a concrete pad footing happening down there. The reason we want to use a concrete pad footing down there is so that we can dynabolt the bottom of that steel pier to the concrete. Dynabolt, chemset, masonry, anchor. Typically dynabolt is going to be used because you can just set out all your piers in that structure and then do your fixing later on. So you drill holes and then install dynabolts, tighten them up. You can also cast those bottom plates into the concrete as well. It gives you a very strong binding, very strong uplift, but there's issues when you're doing your concrete pour, for pouring all those things, to get them all set perfectly is very, very difficult. So retrospective is much simpler. But also, in doing it, pouring your concrete pad footings, you might have one 10 millimeters higher than the other one or so, and there might be variations. It doesn't really matter because you've got sort of 50 mil or so variation you can do with your screw top here. So these piers, very common materials. Probably everybody would have seen sections of SHS before. Square hollow section, Gale 50 by 50 mil square hollow section. You see it in your fencing, etc. You could go to Steel Supply and say, I want 8 of those at 2200, 10 of those at 2100, and they just cut a whole bunch for you. There you go. It's fairly cheap stuff. And then tech screws for your adjustable tops in the top of that. Stops termites getting through there. It can be adjusted when you're on site to get everything dead level, but then it can also be adjusted for later on through the life of the building. So you get some movement and some settling over time. You can then, a year later, you can go back in there and you can adjust these. You go, I want to pick this one up and drop that one a little bit. So that's your adjustable steel piers. You are going to want to use those adjustable steel piers on top of something like a concrete pad footing, or you could use them on top of a diamond pier, because that diamond pier has that section on top for specifically designed for fixing like that. And then this is used with a steel frame flooring system, but you can also use that with timber. So with your suspended floor, the way you design, particularly in this scenario, is from top down. We want to know what's happening in our roof, to know what's happening in our walls, that then tells us what's happening in our floor in terms of point loads. So loads that are imposed all the way down. Then, when we know where our point loads are and our width of floors, etc., then we can work out where our points of support need to be for our elevated structure. And it's always going to be an interplay between, do we have really deep, strong beams between points of support which are spaced a long way apart, or do we go cheaper with the timber and have more points of support within that? That's always going to be an interplay of what sort of soils you've got and how much each of those points of support are going to cost you. So if those points of support are going to be if you've got very stable soils, you're just using 50 by 50 SHS for your piers with adjustable tops, then it's probably going to be cheaper to have spacings of around 1500 millimeters per pier. If you've got very reactive soil, you need to auger concrete piers right down into the ground, then it's probably going to be cheaper to have less of those points of support, stronger, thicker bearers in your timber. So as mentioned before, with your timber floors, you've got your piers happening. So these are your pier locations happening in those grey circles like that. Then you install your bearers on top of those piers. And then between or on top of those barriers, you run joists. So your joists are run perpendicular to that. Next week, actually, we've got half an hour yet. What's that? Oh, that's right. I think that's it. Sorry. Yeah. So we've got 6 minutes. So I won't be. So I've got a timber. I've got a whole timber floor little model that I'll bring in. So I'll bring that in next week for going through all of our timber. So we'll go through timber and steel flooring systems, and then walling and roofing structural systems. So I'll bring that model in then at that point. But as a bit of an introduction, we've got our bearers and our joists. Now, for some of the steel frame flooring systems, you've got bearers in the same line as your joists. So you've got, I'll draw it here like this. That's your big solid bearer, and then your joists are joined on to your bearer with some sort of joist hanger like that. That's all very much in the one plane. Or you can have systems whereby your joists sit on top of your bearers. You end up having deeper. Yeah, I think next week we're going to be covering things like single spans, continuous spans, the implications of all of those things, the engineering side of that for making those decisions about your flooring system. But in a nutshell, your floors are made up by bearers that take a lot of the load, that get it onto your piers, and then joists which transfer their load onto your bearers, and they run perpendicular. I'll leave it at that in terms of all your different. Well, okay. Now we'll quickly touch on. So we understand strip footings fairly well. Strip footings are these independent strips of concrete that transfer loads to soils. Really only good in stable soils because they're all happening. They're not tied together. They're all happening independently. And also I mentioned a grillage raft earlier on as well. Show you these details of a grillage raft. Grillage raft, same sort of thing as your raft slab, except as I mentioned before, your beams are much deeper. So you might do something like that where you've got, load-bearing soil down quite deep in your soil profile. Or you may do that where you've got a lot of reactivity, you want a lot of strength in those beams. To create the strength in those beams, you make them really deep. Places around Adelaide where you see grillage rafts used, Ross Trevor Newton area. Anybody know the soil around Ross Trevor Newton? No, it's fantastic for growing on, terrible for building on. It is really reactive. So takes in a lot of moisture, but then it's highly reactive soil as well. So around there you see grillage rafts being built in there.
So they use that grillage raft that's part on kind of slab.
Yes, that's a kind of slab. It's like a raft slab on steroids. So it's a raft slab with beams that are really deep. They might be 1,200 millimeters deep or something. Whereas typically your raft slab is going to have beams around 700 mil deep. So grillage raft, and then your strip footing. That's the rest. Well, that's all for the concrete section. Now,